Good afternoon. Okay. Okay, good afternoon to everybody. My name is Paolo Roccetti, and I'm pleased to start this session on the cybersecurity of AI-powered system at the BDBA Data Week 2022. So thank you for joining the session, and thank you for attending it. So I will introduce myself first of all. So I'm the head of cybersecurity research unit at Engineering Informatica. I'm part of IS3 Lab, which is one of the 4 laboratories, research laboratories that engineering has. We focus on cybersecurity research project, of course, both national and EU funded. And those that you can see in the slide are 3 things that are keeping me busy during this period. So first of all, I'm coordinator of CyberSeas project, which is a H2020 project focusing at improving the overall resilience for electrical power and energy systems. Here at the link you can find more information. Then I'm also co-chairing the EXO working group 6.2 dealing with digital transformation in verticals, and we kicked off last year a cluster named CyberEPS, which focus on the exchange of information to improve the resilience of electrical power and energy systems. Just to describe in a nutshell what are the focus of our laboratory. We work to innovate the engineering offer by conceiving, designing, developing, and demonstrating new concepts and solutions in a number of domains that covers from industry, agri-food, transport, security, and defense. So this is a nice picture of the domains we cover. And we have more or less more than 50 running projects, research projects. So in short, we are part of this large laboratory that is one of the 4 engineering have. So moving on to the purpose of this session, why session on cybersecurity of artificial intelligence and AI-powered system? Because in short, the usage of AI technologies and so the creation of AI-powered systems is becoming one of the enabler for the processing of large amount of data. And so they are at the bottom, at the ground of enabling data-driven processes. And for this reason, the security of those technologies, and in particular the security of AI-powered system, is then becoming crucial and critical in order to protect and ensure the continuity and reliability of those processes. So what I show here is a nice picture from Gartner that shows how the number of AI-based or machine learning-based projects doubles every year. So it's really becoming pervasive within every domain and in many domains. So this is really something that we need to take into account. The cybersecurity of AI is something that is becoming critical. So this is the agenda for the workshop. After my welcome and session overview, then we have 4 speakers. First of all, Samuel Marshall from WithSecure will introduce the machine learning security with a technical overview and challenges related to it. Then Hazukan from the University of Waterloo will talk about conflicts between machine learning security and privacy. Then Marcus from TU Darmstadt will introduce the promises and pitfalls of collaborative AI, especially on machine learning, federated machine learning. And then, last but not least, Battista from Pluribus One will talk about machine learning security, the lesson learned, and the future challenges. The workshop will be closed by a moderated session with discussion and questions. So before I leave the floor to the other speakers, you have to note that you can interact live with the session. So you can post questions and comments in the B2Match chat, which you will find at this link. And the questions will be collected and then asked to speakers at the end during the final the discussion at the end of the workshop. So thank you very much for attending again. And I'm leaving the floor to the first of our speakers, to Samuel Marshall from WithSecure. Samuel, the floor is yours.
Thank you, Paolo. There. Okay. So I'm Samuel Marshall, and I'm a senior data scientist at WithSecure, where I lead a research team actually that focus on the security of machine learning systems. And today, I will give a high-level overview of what is machine learning security and some of the challenges that we would face to tackle security threats in organizations. So actually, Paolo already illustrated why should we care about machine learning security. So of course, machine learning start to be used in many more applications, and also it start to be used in larger systems. And having a machine learning component, if it's not secure, can compromise the whole system. So that's why we should have reliable machine learning models in larger systems. Also, one thing that we should really take care about is that there are new security threats and attacks that are specific to ML systems, and I will talk a bit more about this. Also, there is very little expertise at the moment. Actually, either in machine learning and security, and even less at the intersection of both. So the expertise in machine learning security is very low. So yeah, there are many things that we still need to discover about this problem. And the last motivation is that maybe some of you have noticed that there is an emergence of regulation around artificial intelligence and machine learning, and especially the AI Act proposed by the European Commission presents some requirements about performance and security of machine learning systems. So yeah, all these things point to the fact that we should care about machine learning security. So to start understanding why is machine learning security or security of machine learning system particular, we should look at the difference between a machine learning system and traditional system. So here you can see a machine learning pipeline with the collection of training data, training the model, then getting the model and getting it to provide prediction or this inference process or generating data. And I highlighted in a yellow or orange a bit the difference that you have in this machine learning systems compared to other systems. And that's why we will have specific vulnerabilities in machine learning systems. So the first particularity is that at the beginning and end of this pipeline, you have this data. So data sources and data input for prediction that are taken from the environment. And actually, this means that we can compromise the system by manipulating the environment. And it's very difficult to specify what are valid inputs and invalid inputs in the particular case of machine learning pipelines. And actually, that's why we have machine learning model, because often we cannot define what is, what is valid and what is invalid. And we can just provide everything to this machine learning model, and it will tell us what it is, this data. So this means that actually compromised inputs are very easy to generate, and they will be by default accepted by the machine learning model, but still they won't have the behavior that we expect. So this is one first difference. So this data that is taken from the environment and that can be easily manipulated. A second particularity is this use of pre-trained models. So, of course, we will use external library to train our machine learning model, but also often the knowledge learned by existing machine learning model will be used as a basis to retrain a model that will have a different purpose, a different task. And at this point, it will be very difficult to determine if this model that comes from outside and may not be trusted, is it compromised or not? While we can do this quite easily for traditional code and existing libraries, for pre-trained models, it's very difficult to know if it's compromised or not. And we have a high chance to take compromised model as basis to retrain our model, and our model will also be compromised thereby. And the last particularity is this link that you have between training data, the machine learning model, and the prediction that it provides. So some information about the training data is always embedded in the machine learning model, and also it will leak into predictions. So that means that it's very difficult to protect like sensitive training data. Even though it's very well protected, this training data, by exposing the model, we can leak information about this data. So preserving data confidentiality is very complicated in this use case. So those are the three characteristics. So yeah. And this leads to having some machine learning, so attacks that are specific to machine learning systems. And on a high level, we have like four categories of attacks. So the first is model evasion. So these inputs that are crafted during inference and that will be misclassified by the model. So they will fool the model on purpose. Then model poisoning is an attack that is launched during training of the model, and by putting adversarial data in the training data of a machine learning model, we can cause it to have a skew in its prediction when it will be deployed. The third attack is model stealing, and here, so it compromises the confidentiality of the machine learning model, and we can uncover machine learning models by just probing them with inputs and getting their prediction. And the last one is data inference. So this compromise of the confidentiality of the training data. So by getting access to the machine learning model or its prediction, we can actually infer information about private data that was used to train the model. So four attacks that are specific to machine learning systems. And I wanted to illustrate some of them. So yeah, attacks that have been demonstrated against a real machine learning system. So 2 model evasion attacks, 1 model poisoning, and 1 data inference attack that I will present to you. So the first one was an evasion of malware detector for Android malware. So this silence antivirus that was a machine learning prediction model that decide if an Android application is malicious or not. And this machine learning model is just trained with string features extracted from Android applications, and they are input to the model, and based on that, the model makes its decision. And by reverse engineering this model, researchers were able to identify a string patch that is indicative of just good application, and demonstrated that by using this universal patch of string and adding it to any malicious Android application, you can just turn the decision of the malware classifier from malware to benign application. And so here you can see on the right side the score before injecting this string patch, which is always negative, and in red indicating of malicious application. So for several malware like CoinMiner, Drydex, Emotet, and so on. And just by adding this patch that has no impact on how the malware function and its utility, so it's still malicious application, you can turn, so yeah, all these score actually very close to 1000, which is a perfectly benign application. So this is an example of how machine learning model, so here malware classifier, can be evaded. Then another example of evasion attack is against those Tesla-like autopilot, and they have this image classification model, or like object recognition model, to detect those lanes. And here again, so researchers have demonstrated that so you can make lanes disappear just by adding some blur. So blurring them, as you can see on the top picture in the right, will make the lane not detected by the detector anymore. And what is even more concerning is that actually you can see in the bottom image, so actually you don't see much, but by adding just some dots on the street, you can actually make the detector detect a lane that does not exist. So yeah, well, so these autopilot basically follow the lanes, and they will just, well, you can basically bring a car like to yeah, to the other lane using this kind of attack. So then an example of poisoning attack against this Microsoft AI chatbot that is called Tay. So Tay was a chatbot that was deployed on Twitter. So, and its purpose was just to interact with a normal Twitter user. So yeah, making tweets, replying to tweets, and so on. And well, actually, it worked pretty well during one day or so. But the problem is that actually this chatbot was retrained with tweets that other users were posted to it. And one issue is that actually those tweets were very opinionated, and well, so like yeah, racist tweets or like machist tweets and so on. And so this chatbot just became the same as the user that were interacting with it, and it became it started to make so racist tweets and yeah, tweets against feminists and so on, like a short time after it was launched. So this is an example of poisoning attack where if you feed a model with just bad data, it will pick and learn on this bad data and not have the behavior that you expect. And this was actually real attack against a real deployed system in this case that was live. And then a last attack, so it's this compromise of the training data and this inversion. So how to uncover data from a model, like the training data of a model, by only having access to that model. And this was demonstrated against this auto-completion system that we can have on smartphone to complete our text message, or also on emails. And here, actually, Gmail has this function that when you start typing a sentence, it can suggest what is the end of the sentence, and you can just, by pressing tab, just feed it and agree with the model if it's what you want to say, actually. And these models are actually trained with real emails. And one issue is that actually, if you have sensitive information in those emails, like where here the example is a social security number, and if in your emails you maybe type in similar occurrences several times your social security number following a certain sentence. So then if an attacker can just find the beginning of the sentence, it will get the rest of this sentence, and maybe infer your social security number. And here you have the example, so on the bottom right, where you start to type this sentence. So Nicolas' social security number is, and if you find actually here the 3 first digit of the social security number of that person, then the model will just give you the rest. So it reduced drastically the search space, like going from 9 numbers actually to only 3. And here you will get a confirmation that this is likely the real social security number, because the model will predict it. So an example of data that is leaked from the model without having access to the original data. So I hope this convinced you that, well, those attacks can happen in the real world and against real systems. So 2 examples of evasion attacks, one of poisoning and one of model inversion, even though actually this is not really an attack. It's just looking at what the model predicts or generates. So now to conclude, I wanted to go through a few challenges that we have to address if we want to deal with those ML security threats in organizations. So the first challenges are technical challenges. So actually, it would be nice if you could defend against this attack, but at the moment, there are no foolproof solutions to defend against any of the adversarial machine learning attacks. So there are defenses that exist, but they can only mitigate attacks or reduce their effectiveness. And in most cases, they are very specific to like specific machine learning model or specific task, and they do not generalize very well. Another issue with this solution is that often, well, they come with a trade-off and they impact the performance or the accuracy of the model. So adversarial training is a very good technique to protect from evasion attacks, but it reduces the accuracy. Also, differential privacy protect to some extent to data inference, but it also reduces accuracy. Also, some research have claimed that some of these vulnerabilities, so for instance, the vulnerability to evasion attack is a feature of machine learning system. And if we want to keep the good performance, we have necessarily some vulnerabilities that will remain. So it seems that maybe there is no way to cope with these vulnerabilities like 100%. So this is the first challenge. Then so actually something that Ashokan will talk a bit more about is that there are conflict between different security and privacy requirements. And when we want to get, for instance, resilience to evasion, we will have to compromise with other security features. So yeah, for instance, the resistance against evasion attacks often includes the vulnerability against data inference attacks. Also, data privacy protection can ease model poisoning attacks because, yeah, if we want to protect more the privacy of the data or of the model, we have no means actually to detect if it's compromised. But even more concerning is that, well, also security conflicts with many other AI requirements, so beyond security and privacy. And yeah, for instance, the European Commission talked about this trustworthy AI and lists several requirements for this. So like accuracy, explainability, fairness, transparency, and also security is included. And well, it's the same. There are some trade-offs. So security almost always compromise accuracy to some extent. Also, explainability is in trade-off with security and privacy. So yeah, security requirements and other AI requirements conflict between each other. So this makes it very difficult to address this threat. And there are also organizational challenges. So the first is the lack of awareness and concern about the security threats. So at the moment, I think, well, many organizations just find out that, yeah, we can do a lot of things with machine learning and their focus is how to best exploit it. And well, security just come as an afterthought because actually there is already a lot of work on how to get the best out of machine learning for different use cases. Another challenge that we see is that at the moment there is very little reports about actual attacks against machine learning systems. So I presented a few of them just before, but actually there are not many more if you look around. And there can be several reasons for that. So maybe they are not just happening yet because they are not cost effective for attackers. Maybe also they can just go unnoticed because they are not like much monitoring, like security monitoring of machine learning systems. And well, sometimes also bad accuracy is expected and we don't know that it may be linked to an attack. Or the last option is that maybe they remain undisclosed because, yeah, well, organizations don't want to share that they are vulnerable to some attacks. And even though they notice some attack, they won't talk about them. Another challenge is that actually traditional security, so like system security, is still quite separated for ML security, and approaches for security are not integrated together. So security risk assessment, vulnerability assessment in threat modeling usually do not consider that machine learning systems have specific threats are targeted by specific attacks. And so now there is no comprehensive modeling of threats against machine learning based systems. Another challenge that I already touched a bit upon is the difficulty to staff ML security experts. So yeah, there is already a lack of security expert and also machine learning expert, data scientists, and well, there are very little experts in machine learning security, and also there is not much training and education to have ML security expert, and usually machine learning studies and security studies are very well disjoint and they have no overlap. The last issue is related to security ownership, and actually at the moment there is a bit of misunderstanding on there. So who should be responsible for the security of machine learning systems? So library providers that should make training library secure, the deployment platform. So if you deploy your machine learning system on AWS, for instance, so should they be responsible, or just the trainer of the model, the developer and the owner? And actually, at the moment, most ML developers think that libraries are secured. So yeah, the libraries that you find and use to train your model are secured, while actually they are not. Like none of them have some security feature against to protect from machine learning attacks. And yeah, so that's what I wanted to present, and that's my last slide. So yeah, if you have any question, I will be happy to take them in the end. And I think that now we can turn to Ashokan for his talk.
Thank you very much, Samuel. So I will leave the floor to Ashokan for his presentation on conflict between machine learning security and privacy techniques. Ashokan, the floor is yours.
Thank you, Paolo. So thank you for the invitation. I'm happy to be here. So I'm going to talk about building on what Paolo and Samuel had said. So they had convinced you that A, machine learning is very widely used. It's going to be pervasive in all aspects of life. And B, there are various security and privacy concerns that arise in systems that are based on machine learning. So I'm going to talk about the conflicts between these preventive mechanisms that one can deploy. And the title may be a little bit misleading. So I'm not going to talk about the conflict between security versus privacy. Some of them is that, but also within security techniques or within privacy techniques. So let me start by introducing myself. My name is Ashokan. I'm a professor at the University of Waterloo in Canada. I also hold an adjunct position at Aalto University in Finland. And this is joint work with my PhD students, Sebastian Schiller, who is a PhD student at Aalto University. Samuel already mentioned model stealing or model theft. And I think he briefly mentioned why is this an important concern. This is because, as we all, I'm sure, agree, machine learning models represent an enormous economic opportunity. And therefore, people who spend a lot of effort and time to build machine learning models and monetize that rely on the business advantage that these models bring them. And these, in a sense, these models also constitute the intellectual property of the effort and expertise that they put into that. And this gaining this business advantage comes with an associated cost. And the cost can be in gathering relevant and useful data, cleaning them up, and so on. And then for supervised training, for classifiers, and so on. And important source of the cost is to label the data so that you have a basis for training the models. And then you need expertise, like Samuel mentioned, to figure out what's the right model, what's the training method, and so on. And finally, the resources expended in the actual training, the CPU cycles, the memory, and so on. And then you know that some of these now very popular models require so much resource and effort to train that they are really beyond the reach of small-scale developers, companies, or academics. You need the resources of very large corporations to be able to train those models. So this is where the incentive for model stealing comes in, because if OpenAI trains this fantastic DALL-E model and they want to monetize that, and somebody wants to offer a smaller model, they have an incentive to steal that model as to avoid the cost that OpenAI sunk into building that model. And we have known this from other domains like the internet or software in general, that initially when systems are designed and developed, the people who have the expertise in those specific areas don't actually think about bad actors behaving with malicious intent. But once those technologies become successful, they invariably attract bad actors. And the same thing will happen to machine learning-based systems in general, and the case of model theft in particular. Once the bad actors realize that there's economic value, they would want to engage in attacks like model stealing. So this is the rationale why model stealing or model theft is an important concern, and why it's necessary to figure out ways of protecting them. There are different ways in which a model can be stolen. I think Samuel mentioned one of them, which is if a model is made available to legitimate customers via some kind of inference interface. Like think about Google Translate API. Google keeps the model somewhere and then allows you to use their model by providing an API that you can build into your software or even access it directly via the web. So model extraction refers to an adversary who uses only this API and query this target model repeatedly, and essentially using it as an oracle, so that gather a little bit of information each time, and then use this information to build a so-called surrogate model, which hopefully, from the adversary's point of view, has the similar level of functionality like the target model. That's called black box theft or model extraction. But it might also be that the model is just stolen directly, right? So maybe the adversary breaks into your system and steals the bits and bytes that constitute the model, or you sell the model to legitimate clients and put some kind of terms of usage or terms of purchase agreement that says they should not be redistributed, but they somehow extract the models from your software package and try to undercut your business by using that model to offer a competing service. That's referred to as white box theft. In fact, there's a paper in a top conference in security, a security conference this year, that shows how this kind of models can be just extracted like white box theft from Android applications. So many Android applications have come with built-in models, and they show that by using various techniques, they can just take the model out of these applications and then use it for various purposes. So how do you go about defending these against this model theft? So ideally, one would want to prevent or detect it. But really, prevention or detection isn't relevant in the case of white box theft, or in a way, it's sort of out of scope. If somebody breaks into a machine and steals the bits and bytes that constitute the model, then preventing against that is in the domain of sort of standard system security. But also, it turns out that it's not easy to prevent or detect even sort of black box theft, meaning this model extraction. So this is where you offer a service, they offer you model via an interface, and then the attacker tries to steal the model by accessing it via the interface. So there is, one would think that there is some hope that either detecting that and preventing it during that attempt to steal. But I think Samuel already alluded to this, that it is really hard to define what constitutes sort of legitimate queries to your model and what constitutes potential attempts to attack it, in particular to steal it. So ideally, prevention or detection is the best, but it's only applicable for model extraction, and even there, it seems it's hard, if not impossible, to do so. But the other approach to defense can be deterrence, meaning that you don't try to prevent or even detect whether your model is being stolen, but you try to remove the incentive for the attacker to steal it. And again, this is relevant only if the goal of the attacker is to steal the model and then to offer a competing service that would undercut your business. Because the way these deterrence is done is by ownership demonstration. That if a model shows up somewhere, say on the internet, and you suspect that this is actually stolen from your model, then you can demonstrate that by using some sort of ownership demonstration technique. But the prerequisite for that is that the attacker takes the stolen model and then exposes it by offering a competing service. If the attacker just keeps the stolen model for their own use without exposing it to anybody, then this deterrence isn't applicable. So think about this in the terms of, say, watermarking of some digital media or any media for that example, right? So if watermarking is a deterrence, if the attacker who stole your media is going to expose it in some way, like they're going to try to sell it in the market or try to put it in a museum or something like that. If somebody steals your valuable painting and then keeps it in their basement, deterrence isn't an effective technique. So here you're focusing on deterrence as a technique against adversaries who steal your model for economic reasons where they want to undercut your business. And there have been different techniques that can be used as a deterrence mechanism by demonstrating ownership. And they fall into two broad categories: watermarking or fingerprinting. Watermarking means that you somehow change the model that you want to protect by either adding training data or adjusting the model in some way, so that if this model then shows up, or some model derived from this watermark model shows up somewhere, you'll be able to demonstrate that it is derived from your model. The second technique is fingerprinting, where you don't change the model in any way, but you try to extract something that is inherently characteristic of that model, like a human fingerprint. And again, if the model then shows up, or something that's derived from the model shows up somewhere, you'll be able to use these fingerprints that you have already established to show that it is derived from your model. In watermarking, you can think about two different categories of watermarking. You can watermark the model, meaning that then if the model is stolen, then you want to show that it is derived from your original model. Or the data can be watermarked, meaning that you'll be able to show that any model that is trained from your data can be established as having been trained from your data. So these are the different categories. So of differences. So in the last 5 to 7 years, this has been a very popular area. Many academics, including me, my collaborators and my students, as well as many others around the world, have been looking into model extraction as a threat and different ways of defending against that. And this is not limited to model extraction. All the sort of concerns that Samuel mentioned, there had been significant amount of work looking into both attacks and defenses. But by and large, academics have been focusing on single issues. So people who are working on model extraction will think about model extraction and think about cleverer ways of extracting models, or even cleverer ways of defending against that. But then these single issues are, while it's important to study them, there are, of course, different single issues, like Samuel pointed out. So Samuel mentioned model evasion, which is how can you manipulate the input that you send to a model in a way that you force the model into taking the wrong conclusion, like classifying a picture differently and so on. So again, this has been studied extensively. I think Batista, who will be talking later, is one of the pioneers of this area. And there have been many different kinds of defenses that have been discussed against model evasion, such as adversarial training, where you train your model with some examples of inputs that can that can evade the model, and then hope that that inoculates the model against model evasion. Similarly, Samuel mentioned privacy of training data, and the ability of an adversary by interacting with the model to reconstruct the data that was used to train the model. This is a concern. And differential privacy is perhaps the well-known technique against this. The whole field has been sort of silo-wise, so that people have recognized that there are many different concerns, and they have been studying these independently of each other. But if you are a practitioner who wants to deploy, who wants to protect your model, as you can imagine, you probably are concerned about all of these problems, and you probably want to secure your machine learning model simultaneously against model invasion, against training data reconstruction, while at the same time building in ownership demonstration techniques. And I mentioned two of them, and these other concerns that I'm going to talk about, but there are other concerns as well: membership inference, model poisoning, and so on. So the central question that arises from here is, while it's useful to study these techniques, these problems independently, one has to ask, how do these interact with each other? Because practitioners want to deploy two or more of them simultaneously. And this is the main message. So I could effectively stop here and say, this is an important concern, and people should go beyond studying individual problems and study sort of how they interact with each other, whether defenses against one will harm the other, or whether it's not sensible to take the best defense against the best watermarking technique and the best differential privacy technique, because they're going to interact negatively, but you need to find something that is sort of less than the perfect defenses, which might actually work well together. So in the rest of my talk, I'm going to give you some examples of the explorations that we have done, in particular with these three cases. So we looked at model watermarking, data watermarking, fingerprinting. All of these are ownership verification techniques, and looked at how they interact with differential privacy, which is a technique against training data reconstruction, and adversarial training, which is a technique against model evasion. But I want to sort of reiterate that the general problem is bigger, and that is with regarding the interaction between any two machine learning security or privacy techniques, and not only two, because as a practitioner, and if you are Google, if you're a small startup who want to deploy a model, you probably want to deploy multiple of these models, and you want to make sure that they don't interact badly. So like I said, this is the take-home message, and the rest of my time, I'm going to quickly walk you through some cases that we have looked at, but those are details. And if you were to take one message from this talk, it is this fact that currently known best techniques can potentially interact badly. Therefore, this needs further study, and that might result in adjusting what is considered as the best possible defense for each problem, because these defenses have to coexist together. So we looked at 5 different techniques. 3 of them are ownership verification. So the first one is watermarking, in particular out of distribution vector watermarking, meaning that you take each image and then insert a watermark that is not from the normal distribution of data that you find for in that particular problem, and then use those out of distribution samples or changes as the watermarks, so that if you want to test against a model that you find out in the open, you would use these watermarks. Second is a technique called radioactive data, which is from Facebook. And this is a dataset watermarking technique as opposed to a model watermarking technique. So they add some or change the dataset in a certain way so that any model built from this can be detected as having been built from the data by looking at aspects like loss difference. Dataset inference is again an academic work that takes an advantage of the asymmetry between the attacker and the defender. The defender knows the entire data set, and therefore they could build ways of sort of, given a model, they could develop a technique that can infer the data that was used to build the model, hence the name dataset inference. And because they know the entire data set, they can do this more effectively than an attacker might do otherwise. we compare these with a differential privacy technique called DPSGD, stochastic gradient descent, and an adversarial training technique, which is intended for strengthening your model against adversarial example. So as you would expect, first we took these implementations, these techniques, either from the original sources or re-implemented ourselves, and sort of convinced ourselves that these the techniques that we are going to use in our experiments are in fact reasonable defense techniques considered alone. So we looked at 3 data sets, each of them has some level of accuracy, and then we deployed each of these defenses and showed that these defenses have, first of all, the defenses are good. So for example, for watermarking, you look at watermark accuracy, which is reasonably high, but also that deploying this defense alone doesn't harm this test accuracy compared to the no defense test accuracy. So we did that in each of these cases, and you can see that in most cases it's reasonable, except in the case of differential privacy applied to this one particular data set where it destroys test accuracy. So one could argue that there's no motivation for the attacker to steal this model because the test accuracy is bad. But by and large, these techniques work as advertised. So the first experiment was how would the dataset inference, the ownership verification techniques interact with differential privacy. So again, I'm not going to go through each of them, but I just want you to sort of see the pattern. So in the slides that I'm going to show, the general pattern is like this. So you see the baseline here. So this is differential privacy applied by itself. This is the same kind of table that you saw before, the no defense accuracy. But now for each of the 3 ownership verification techniques, we show the baseline where that technique is applied alone. And then we say how the interaction with dataset, the differential privacy manifests as. So those are these 2 columns that says with DP. And you can see here that watermarking, backdoor-based watermarking is completely destroyed if you combine that with differential privacy. So red numbers are bad, green numbers are good. Radioactive data with differential privacy is still valid, but greatly diminished. So positive numbers here are good, and with differential privacy, the loss difference numbers are still positive, but much less compared to before. Dataset inference, on the other hand, is still seem quite effective. So we looked at different ways of changing how you apply dataset differential privacy with these ownership verification techniques. None of these are really effective in resolving this conflict. So we can sort of conclude that with strict differential privacy, watermarking simply doesn't, backdoor watermarking simply doesn't work. So I want to give you a similar thing with adversarial training, interaction with adversarial training. Again, the pattern is the same. This is the baseline adversarial training. And then for each defense, we show how adversarial training impacts. And adversarial training with watermarking or radioactive data is effectively renders it useless. Dataset inference still seems to be good. So we dug a little bit further into dataset inference, and we noticed that even though the numbers are good, they still generate false positives, meaning that even if a model that is trained not from the original data set that the victim owns, but from a different data set, this technique would still flag them as potentially a stolen model. So I will not go into these details saying that that's a particular blip in that particular technique. But by and large, I think this dataset inference can still be an effective defensive mechanism as a general principle. So we had some experiments to show that there may be still promise in dataset inference, including tweaking the particular training technique that we saw earlier. So I'm not going to go into details, but I just want to put up the big picture again. The big picture is not about the specific techniques that I showed you, but the fact that we want to have different properties guaranteed by different defenses. And there has been very little exploration of how they interact. We looked at some of them. There have been some work in the literature addressing some other concerns, but you see that this matrix is very sparse. So there are many questions marked here. And this is still talking about pairwise interaction. So I would leave you with this, this sort of thought that these examples that we show that the interaction is negative, but the research community should recognize that practitioners have a need to deploy 2 or more of these defenses simultaneously. We just looked at 3 pairs, but there are many, many more combinations, and even worse, we can't even stop at pairwise combinations, but you have to look at triplets and quadruplets and so on. So in a way, this is a call to action for the R&D community, that this is a problem that's waiting down the line, and therefore it's fruitful to look at these conflicts and try to resolve them by adjusting the techniques. So I'll stop here because I am out of time, but I'll be happy to answer questions later.
Thank you very much, Ashokan. Now I leave the floor to Markus from TUM Darmstadt, which will talk about promises and pitfalls of collaborative AI in view of backdoor attacks. So, Markus, the floor is yours.
Yeah, thank you. My name is Markus Miettinen. I'm a postdoctoral researcher at the System Security Lab of Technical University of Darmstadt, and focusing mostly on IoT security and also security of AI and use of AI for security functionalities. And to connect to the previous talks, I will dig down a little bit on a particular aspect that this new kind of paradigm of collaborative AI brings with itself, because it opens up kind of a new types of attacks that can affect AI systems. To start, let's have a look at the background. So what is happening is that the world is increasingly getting connected. So the Internet of Things causes many new application areas that previously have not been connected to be connected and to generate data and communicate with each other. And this, of course, provides great possibilities for creating new functionalities and building in intelligence into the system. Since there is a lot of data available, you can optimize many of these systems if you use AI reasoning. However, it's kind of obvious that there there's this traditional way of doing doing AI, where basically you collect all the data into a giant data center and have big servers running big algorithms and produce results. However, in this kind of massively networked world, this might not be feasible or economic. So in recent times, this kind of new algorithms doing collaborative AI have emerged, where basically the algorithms are distributed into the edge networks. And this has obviously many benefits. So you don't need to collect all this data into a central place. You don't need to store it. The communication overhead is much less. And you also have this possibility to do the parallel processing at the edge. So you don't need these massive data centers. One particular kind of approach that is very popular in recent times is what is called federated learning, where basically a number of clients collaborate together with the help of an aggregator to use their common data to train a joint model. So works like this, so that each client has their own local data sets, which they use for training the models and produce local models, so to say. These local models are then communicated to an aggregator who basically does an aggregation of these models, generating a global model that is based on all the data provided by the clients. This global model, can then be distributed back to the clients, who can then use it locally for inference purposes, for example. This has, of course, many benefits, meaning you can very quickly learn accurate models because you have much more data available. You are not limited to your own little data set, but you can also utilize the knowledge in other clients' data sets. This also has privacy benefits. So obviously, you don't need to share your raw data set with anyone else. So only the model is shared. So this reduces kind of your exposure to exposure quite drastically. So as the raw data are not shared. Of course, the models themselves do leak some data, but or some information about your training data sets, but at a much lesser extent. There are numerous applications where federated learning can be applied. We have worked on a IoT intrusion detection platform utilizing basically federated learning for generating detection profiles. One very big application is the Google's Gboard, which is used for text prediction on mobile phones. And federated learning is also being used in the medical area for kind of medical image processing. So it's a kind of a big and growing field, but what about security and privacy in this setting? The problem with such settings is that there are new attack vectors that can, or you are more vulnerable to certain types of attacks. Since the clients are not under the control of the aggregator, the clients, if they are malicious, they can do a lot of things. So for example, they can do what's called data poisoning, so inject crafted data or specific data that tries to influence the model in a negative way. Or they can even directly manipulate the models that they create and try to manipulate the model in a way that the manipulated model will have an impact on the aggregated global model. And of course, the model inference attacks are also possible. However, I'm not focusing on that aspect in this talk. So yeah, basically there's two main types of attacks on federated learning. One is kind of sabotage attack, a denial of service attack, where the adversary just tries to make the model behave badly so that the accuracy of the model goes down. The other one is what's called a backdoor attack, where the model is manipulated in a way that for specific types of input, the manipulated model will provide specific types of output. I will focus now on the backdoor attacks, since these denial of service attacks are much easier to detect, because you can basically, from model updates, you can more easily conclude that, okay, now this model update is messing up with our system, so we can reject it. What would the backdoor attack look like in practical cases? So, for example, in this text entry word prediction application, you could basically train or kind of introduce a backdoor that for specific sentences, the predicted word is a specific word. Or in image classification systems, you could cause the misclassification of, for example, traffic signs in autonomous cars. Or in IoT malware detection, you could basically inject malicious models so that a specific type of attack is not detected but considered benign. There are some defenses already in the research community looking at these kinds of backdoor attacks. And in general, AI securities in the security community are a very hot topic and target of ongoing defense research. One major group of defenses is anomaly detection based, where basically the aggregator looks at the model updates it gets from the clients and tries to cluster them, for example, and try to identify models that look significantly different from the majority, which is assumed to be benign. However, many of these approaches that have been proposed, they make quite strong assumptions about specific properties about the data distributions of models or the underlying data. And as said, there is no kind of really effective solution yet against state-of-the-art attack methods where the adversary actually tries to avoid being detected by, for example, limiting the amount of poison data it injects into the model. Another approach is based on differential privacy, where basically one tries to eliminate the backdoors or the effect of the backdoor by introducing random noise into these models. And that works. However, the more noise you inject into the model, the worse your performance on the actual task of the model will be. So again, here there is this, what Asokan already talked about, this kind of trade-off between targets, security and accuracy in this case. We are, to give you an idea of what we have been working on in this area, I give you a brief overview of a new type of defense that we have developed together with my colleagues to tackle these kind of backdoor attacks. And it shows that to reach effectiveness, one often needs to combine things to get good results. What is shown here is the global model. So if you, of course, a real machine learning model is a multi-dimensional object that has parameters, thousands of different parameters. So it's complicated mathematical object. But if we now kind of make imagine that the model would be a two-dimensional vector. This would be the global model that has been trained in previous rounds of training, or based on a benign data set to start with. And these blue arrows represent models that benign clients submit into the aggregation process to train the model further. And the observation that we want to make is that there's basically three types of, or roughly three classes of malicious models that an adversary could use to try to influence this global model. So this first one is a model that is kind of very much focusing on this backdoor that the adversary wants to introduce into the model. But due to this, the model also deviates quite a lot from the rest of or particularly from the global model. The difference is quite large. The other possibility is that the adversary tries to train a model that doesn't deviate too much, but has a maximal impact on the trained model. So there is a trick that the adversary can use. He can basically train a model with a modest amount of poisoned data and then scale up the model. This is shown with the length of the arrow, so that basically by scaling up the model, he can have more impact on the aggregated model. And finally, there's then a model, a malicious model that doesn't deviate too much from the other models, but obviously it also doesn't have very much impact. And our defense now tries to combine certain different methods to make all of this work out in a way that the backdoor attack doesn't work. And the first component of this defense is we call model filtering. It's basically doing a clustering of the models that individual clients submit and tries to identify a large cluster where at least half of the clients are. This is because we assume that at least half of the clients are benign, so there should be one big benign cluster that contains the benign models. And any models that do not fit into this big cluster, we consider them outliers and filter them away because those are potentially malicious. And this will get rid of this first type of adversarial models. The second thing is what we do model clipping. So we basically limit the amount or the impact that any of the models can have on the final global model. And we do this just by reducing or clipping the weights of these individual models, the model updates. Finally, when there is an aggregated model, the models have been aggregated, we add a little bit of noise. And this noising will have the effect that any remaining malicious models or the impact of those will be basically averaged out. And how does this work in practice? Here on the bottom, you see number of clients. Most of them are contributing benign models into the aggregation. But there are also two adversaries, one with a kind of well-trained backdoor and one with a kind of less poisoned model. In the first phase, these models, we do this model filtering. So we identify that, okay, this model here, it's too different from the others, so we eliminate it. In the next step, we have the remaining models. Most of them are benign, but we have this one model that is still poisoned, but it's only slightly poisoned. And we even reduce the impact by clipping the weights. This means we get a global model that is that still has a little bit of backdoor contribution, and that is where we add Gaussian noise and kind of are able to eliminate the rest of the malicious impact. To conclude, we performed some experiments with this approach, and as you can see, we tried it out on different types of data sets, Reddit and Cypher data sets, and our own IoT traffic data set. And you can see that in very many cases, the backdoor accuracy can be reduced quite significantly from the case where we do not have a defense. And what is more important or very important is also that the main task accuracy, basically the main usage of the model, it is much better preserved than in other defense approaches. And this is basically caused by the fact that by combining these different defense steps, by doing the model filtering, by doing the weight clipping, we actually remove a kind of large part of the impact of this backdoor models, so that whatever remains in the final step, backdoor impact, we can remove by injecting only a modest amount of random noise into the final model so that the main task accuracy is better preserved. And with that, I want to conclude. So just my main message is that collaborative AI is an emerging trend, and it provides many benefits, especially when more and more processing is happening at the edges of networks. And federated learning is a wonderful tool for creating collaborative AI systems. However, we have these new types of data and model poisoning attacks, and there is a lot of research ongoing there, but I gave you an example of one solution that we have been working on that tries to combine different methods to come up with a practical system for backdoor defense. And in conclusion, then I will give the floor to the next speaker, but we'll be happy to answer any questions in the end of this session. Thank you.
Thank you very much, Marcus. So now I leave the floor to the fourth speaker, Battista Biggio from Pluribus One. Battista, the floor is yours.
Okay, thank you, Paolo, and good afternoon, everybody. Let me share my screen. All right. So, well, it's a pleasure for me to be here, and especially have the opportunity to try to squeeze 15 years of research in 20 minutes, right? So the title of the talk is this one. It's about, again, machine learning security, but I will try to sum up a bit what we have learned during the past 15 years, as I said, and summarize the future challenges. My name is Battista Biggio. I am a founder of Pluribus One, which is a company working on secure AI for cybersecurity tasks. And I'm also assistant professor at the University of Cagliari here in Italy. So, as I said, we started working on these topics like 15 years ago when it was much less popular than today. And this was around 2007 and 2008. And if you were to ask me what is, let's say, the most important contribution that we gave to the field, I would answer that we were the first to formalize, in a sense, optimal attacks against machine learning models. At that time, we were trying to break, the earlier systems used for malware detection that were using AI behind the scenes and machine learning. So the question was, what can an attacker do to bypass these systems? Okay, and by coming from this security angle, we were the first to discover that you can poison models by manipulating few training points, and that you can also manipulate data during operation in a way that bypasses the detection of these malware detectors. However, the field became, let's say, much more popular after this work by Google Brain in 2014, where they discovered adversarial examples against deep models. Okay, so they found that you can actually perturb images by a very small amount, and this can cause images to be misclassified as something different, even if you cannot see the perturbation, as a human. The news here is that in this paper, they do not consider security at all. They were trying to interpret what neural networks learn from data. Okay, so they were trying to understand what you should change in images to have a different classification as a result of analyzing this image. And surprisingly, what they discovered is that this perturbation needs to be very small. Okay, while they were expecting to see a kind of morphing from a school bus to an ostrich, like growing wings, feather, and these kind of things. So it was discovered incidentally as a bug in this kind of operation. And from there, all this field of AI security boomed. And then we have had a lot of papers on attacking and defenses, and you have seen some examples in the previous talks. I just want to point it out that we also try to reconstruct a bit the story of machine learning security and the security of deep learning in this survey paper, which is called Wild Patterns. So if you want to know more, feel free to search for this paper, or also use the QR code that you find on the top right corner of the slides if you want to have some extra information on this. In this paper, we categorized all the attacks against machine learning. I'm trying to keep this updated as new threat models arise. And basically what you see here is most of the attacks that we have been discussing so far. You have evasion attacks or adversarial examples. You have poisoning, where the attacker plays with the training data. You can backdoor models. You can do different things. And then you have all the privacy-related threats as model extraction, model inversion, and even membership inference. Just to mention, this attack panorama that we have. I'm not going to dig into the details of each attack, but in case you are interested, you can shoot me an email or a question, whatever you prefer. And all these attacks have been demonstrated in a different, under different assumptions of what the attacker can manipulate, what the attacker knows about the system, or it doesn't know. So you have white box attacks and black box attacks in general. So that's the overview for attacks. We also have like a new updated survey paper on poisoning attacks specifically and countermeasures. Again, here we try to systematize more than 200 papers on this area, and there is a lot of confusion about which kind of threat models make sense and which kind of threat models are just fantasy of researchers to publish papers. So we need also to say this. And we tried to kind of clarify these things in this recent paper. Now, the question is, what can we do? What I will try to address in this talk is what we can do to make AI and machine learning more secure. And we have already seen some of the possible countermeasures in previous talk, but here I will try to provide a more systematic view, which in a sense goes a bit beyond the idea of testing attacks by using a pen testing or a red teaming approach, right? So we want to see if there is anything more systematic that we can do on this. And for this, I will draw a parallel. I will try to draw a parallel with the classical software engineer that you have. Software engineering now, as you develop code, right? We develop code nowadays with DevOps. So we have tools that help us do versioning and all these automation process like testing, deployment, and so on. And the same is also happening for machine learning. So we are in a stage where companies are developing these pipelines, which are called machine learning operations, which is, let's say, the dual that you have from software engineering to machine learning engineering in a sense. So you have an ideal pipeline is like this: you prepare data, you train your model, you package, you validate, deploy, and monitor. So that's the basic steps. And this pipeline by itself poses many challenges, both from the industrial and the research perspective, the academic perspective, which is how do you maintain these models over time in a very efficient way? So you have to continuously collect data and relabel it, decide when to retrain a model because maybe accuracy is decreasing, how to do testing and validation in a proper way, how to monitor if your model provided as a service work as expected or not, and so on and so forth. So there are a bunch of challenges that arise from here, but also what is really lacking, I think, from the perspective of developing machine learning is that we don't have proper debugging tools as we have for code development, for example. And similarly, we don't have systematic tools for doing security testing of these models, considering threat models which are pertinent for your use case or for your scenario. So the vision that I'm trying to propose here is to complement this kind of development cycle with 3 pillars that you see below, which would add this security dimension to the ML operation cycle. So you have protection of models during an offline protection in a sense, which means I want to build robust AI or machine learning models, maybe doing adversarial training or doing data sanitization if I want to contrast poisoning attacks. But there is a kind of defensive approaches that you can apply offline when you train your model. Then there is security testing, which means how do I measure if my model is secure enough, is robust enough against these specific attacks? And the question here is how to automate this. And then you have monitoring and, in a sense, online protection. So when the model is operating, you can check if it's being abused. For instance, if people are querying your model to steal it, or if they are trying to get knowledge about it, about the training data. So this is like the moment where you can apply this kind of monitoring and online countermeasures. So I think we now have a kind of framework that sort of unifies the position of defenses and security testing in the development cycle. And now we can dig a bit more into the some of the approaches and some of the challenges that are hindering progress in this kind of area. Okay, so we'll start from security testing, which means essentially running attacks against models and see which kind of robustness or security you get out of this process. There are three main challenges, I think, that are kind of hindering progress in this area. The first one is that computing attacks against models is slow. So being very slow or computationally demanding, it's something that you cannot test, in a unit testing fashion. So it's something that you need to, what's happening? Okay, sorry, I was seeing questions in the chat. So this is like something on a line of research. We need to make attacks faster and make them scalable to have a sort of unit testing framework as you have for code, something that can run fast and in a reliable way. As I said, we are lacking debugging tools. Then I will tell you why this is important, because we are relying on empirical evaluations, and these are not always reliable by themselves. So you may tend to think that something is secure while in reality is not. So some defenses have been spreading a false sense of security, and we need tools to investigate when this is happening. And the last challenge that you see here on the yellow circle is about how to generalize attacks across different domains, because attacking a classifier that works on images is one problem. Attacking one classifier that works on malware is a different story, because you have, of course, different ways of perturbing the input data, which cannot be encompassed under the same manipulation. So it's the way I change images is not the same way I change malware. I don't have additive perturbations in malware, for example. So about the first challenge, there is, since the first attacks, so these gradient-based attacks against machine learning, there has been a huge number of papers proposing novel attacks, some of them to be faster or try to break some defenses and so on. And now the current state of the art is about these attacks from, it's called AutoAttack, AutoPGD, ALMA, and we also have contributed to this very recently with this fast minimum norm attack paper, where the idea is basically to have a faster convergence to a very good local optimum that you can work with different threat models, and it's easy to tune. Okay, I'm not giving the details of the paper, it's just here as a reference in case you want to investigate more. This is like where the state of the art of attacks is going. And I think many of these attacks are now kind of saturating the, so they are more or less finding the same quality of attacks. Okay, so the evaluations that you get are very similar, even if the attacks are published and say to be something different. They are in the end finding similar robust accuracy values. So that's one line of research which is active. About debugging tools, what we have been doing is something that helps people understand if the evaluation is flawed somehow. And this is a problem because first of all, you cannot analyze the security of machine learning models in a closed form. I mean, you don't have, in most of the cases, you don't have mathematical guarantees for this. So what you are left with is running an empirical evaluation. You mean you optimize the attack and you test what happens. This process raised the problem that many of the defenses were proposed claiming to be robust, and then they turned out to be not robust. So there were follow-up papers, like where you have the red crosses here. These are papers that show that the previous defenses were broken, actually. Okay, so that they were evaluated badly. And despite you have guidelines and rules of thumb to say how you should perform the evaluation, people are making the same mistakes over and over. Okay, so there are this bunch of researchers, including Nicolas Carlini, who are periodically showing that the evaluations even in top tier conference papers are flawed. So how do we avoid this? Well, the proposal that we had is to develop like quantitative indicators of failure. So these are like metrics that you can check or evaluate when the attack is running or on the model itself to see if there is a potential problem when you optimize the attack. Okay, so this is like trying to debug if the evaluation was correct. I can tell you that, for instance, one of the most problematic issues here is that some of the defenses are just making the attack optimization fail. So it's like the model is too noisy to run a gradient descent on top of it. And so many of the attacks were just failing in finding bad local bad points which are not adversarial in the end. But this can be patched very easily. So it can be detected and patched very easily. And so here we are trying, in a sense, to systematize the evaluation. The last point is about how to deal with different domains. Here, the idea is that this is like something you can do. You have a bunch of optimizers on top. You can use the same core algorithms to optimize transformations on different domains. I'm not giving the full details on how you can do it. It's in the papers. But we have done this for malware detection, working with Windows programs, where the idea is that you can actually trick the file format and adding content inside. And the content that you add can be optimized in a way to fool the classifier. These are just all the possible transformation that you have. Then you can optimize the attacks with different ways. So the selection of content can be optimized in a smart way, like extracting content from benign programs and injecting it into the malicious program that you have, that you want to be misclassified. And we were able to bypass some of the state-of-the-art detectors based on gradient, decision trees and deep models. But also, surprisingly, we were able to bypass some of the antiviruses on VirusTotal. This was quite surprising to us because we just add content without removing the malicious content at all. So the malicious content is there and visible, but just changing and adding some bytes or sections to the executable file, you can already bypass some of these detectors. And here you have some of those companies that say they use deep learning for malware detection. So we have also tried to disclose the vulnerabilities here, but they are doing some, they are resisting the process in a way, but still they are not able to patch it, because if the model is using deep learning for this, retraining on attacks is not sufficient to patch the issue. All right, about protection. As I said, there are offline defenses that you can apply. The most famous one is retraining on the attacks. I'm not giving the details of this, but this works fairly well in some cases. For example, we have had a very successful defense on Android malware in specific settings, but for deep models, it doesn't work that well. So if you talk about image classification or other issues, this is just mitigating the problem, but not tackling it completely. For poisoning attacks, you can actually build much more reliable defenses, because at least poisoning attacks that aim to cause denial of service have to inject few samples that are very much different from the other legitimate samples. So for the attack to be effective, this has to be the case. If it's not the case, then you would need a lot of points to poison the model. But based on this observation that poisoning attacks need to inject very different samples with respect to the training data, you can actually detect this. And there are successful defenses that can be developed in this setting. I have also a couple of sketches on defenses that you can use when you monitor a model. So when a model is deployed, you can actually monitor how it works. These are like online defenses. One is about one idea, because this is some work that we did, but there are many similar approaches around, is to inspect like what happens at different internal representations in the network. And you can spot anomalies at different layers. This is one potential way to detect, for example, attacks that use a trigger to activate a backdoor or things like that. Or you can also use to detect instead attacks which are querying the model, maybe to extract confidential information. You can try to analyze the queries that you receive and see how similar they are or how correlated they are, and if they are coming in a large number and in a short amount of time. Because typically to copy a model or extract some confidential information, you need to query it a lot of times. But I think generically it's about tens of thousands. So this is quite anomalous with respect to the normal operation of the system. So that's like a very quick overview of defenses. Here I have more or less green, where I think we can develop something which is meaningful in practice, like to defend models. So I think we have good defenses for privacy, maybe not for model extraction if the attacker is patient enough, but for other cases you can defend even with the trivial mechanisms that do not provide the complete information to the attacker. You can defend against DOS poisoning quite reliably. It's more complicated when it comes to vector attacks and especially adversarial examples. For this one in particular, I think there are already some impossibility results from the theoretical side. So there is theoretical work that tells that if you want to have a system which is so accurate, like a deep learning model, then you have to live with adversarial examples. So there's no way you can rule them out, essentially. There is a similar result for backdoors, but it's a bit, I have to work a bit more on that to get the real flavor of this work. I think that's what I wanted to say. Here you have, again, in this link, you can find additional material or reach me in case you have any other questions. Okay, thanks a lot.
Thank you very much, Battista, and to all speakers. So now I ask all the speakers to switch on the camera and join me for this last part of the session. Okay, so about the discussion, we got one question from the audience, which comes from Yuri Jamchenko. It is, I think it's particularly for Battista. So the question is that MLOps and any DevOps derivatives suggest feedback. So it concerns the feedback part of the loop. So how do you handle this in your MLSecOps model?
I don't know if I got the question right. So what does it mean that it suggests feedback?
Well, MLOps is in MLOps there is a loop. Okay, so from development to operations, then there is a feedback from operation to the development.
Okay.
So how this extends in your model? I think that's the question.
Yeah, so I don't have a practical answer for this. Consider that these ML operations is just something that is being implemented now. So there are many companies which are offering it as a service or deploying this kind of feedback loop from cloud services, like you have it on Microsoft Azure and others. But from the perspective of security, if it's an internal feedback, is not a big problem. What I think it's going to be helpful is something that monitors the model and understands when there is a drift in the data or something is going badly. And this would provide like the trigger to let you know that you have to update the model. And then maybe rerun the feature extraction part, model retraining, validation to see if the accuracy is still good and so on, and then you deploy it. So I think it's going to be a mixture of engineering practices and machine learning algorithms that help you managing this process. I don't know if I answered the question, but this is something I can tell you which is closely related, maybe.
Thanks, Battista. I don't know if there is more comment from other speakers at this point. Okay. So then I have another question for Samuel. So thank you very much for your introduction. My question is about the question I have is about if there have been serious studies on the industry awareness of potential attacks on machine learning models. And if so, what did those studies show us?
Yeah, so there have been a few studies, at least I'm aware of one that was done by Microsoft, but it was not like very large scale. I think they questioned like around 30 organizations that used machine learning. And well, so there were a few results out of this study. So the first one was that well, as expected, actually, most organizations, like 90%, do not consider the threats against machine learning systems and do not try to protect from machine learning specific attacks. Then there was a study on the attacks. So some questionnaire about which attack was perceived as maybe the most impactful if it would succeed against this organization. And there, so it seemed that the main concern was actually poisoning attacks, followed by model stealing And then these model inversion attacks. So confidentiality of the model, confidentiality of the data compromised, and also, just compromise of the training. So the data is poison and it impacts the accuracy of the model. But beside that, I think Gartner did some study that showed somehow the same result about which attacks were the most concerning. But that's all I know. I think we need a bit more and maybe a bit more larger scale studies to know a bit more how it is perceived.
Okay, thanks, Samuel.
If I can add one comment, and I'm not sure if I can.
Sure.
I agree with Samuel. I'm aware of this work by Microsoft Research, and I also was involved in a couple of papers where we collect questionnaire from companies. And the impression that I have is that there is a lot of confusion about, let's say, classical security aspects and aspects which are related to machine learning security. So when you go and talk to data engineers and others, and you mention ML security, they start talking about crypto and other things which are only barely related to this. So I think there is a problem also of awareness of the problem in companies other than, referring to this. So I completely agree with you. And I also think that the poisoning that they have in mind is not actually the poisoning really targeted to the machine learning models, but it's some, let's say, a side effect that may happen when you have mislabeled data points or things like this.
Thanks, Battista. So it seems okay that there is an awareness issue, and but at the same time, I think that most of the cases you presented, for instance, in the Ashkan presentation, they refer to cases where, for instance, the model were stolen. But do we already have real-time cases for this? Ashkan, maybe in your research, you have some finding to this.
Yeah, thanks. This is a good question. And then, as you can imagine, this is something that people ask whenever we try to, people in the industry ask whenever we try to present our work. So Samuel and Battista already mentioned this Microsoft survey. I don't know if I can drop a link on the channel where everybody would see that. So there's a link to that survey, but also like a larger blog post by Microsoft, and where they said that this model stealing is the second most serious concern. As you can imagine, this is not just machine learning, but as with any security breaches, companies are not eager to publicly talk about them. So the only information you can get about breaches is via indirect reports like this. So I don't know of any place where a company has said, yes, our model was stolen. I don't think you would find that, because this is not, unfortunately, this is not how our industry works. But they have an indirect example. So I can give you a couple of other examples. One I mentioned in my, when I was talking, that there's going to be a forthcoming paper at CCS. CCS is Computer Communication Security in November, where some researchers show that you could steal machine learning models from production Android apps. So it's not model extraction in the kind that we mentioned, but it is model stealing. And developers think that by obfuscating their model inside their apps, they are safe. And these guys show at large scale. I think they analyzed hundreds of applications and showed that they could extract model. There is one other example that I can give you, which is also from an academic paper where researchers from Berkeley, I'll put the link here, they were able to extract Google Translate. And they estimated that it cost them something like $12,000 to extract a copy of Google Translate. Their goal was not to use it for translation, but to actually find adversarial examples against Google Translate. And the adversarial examples they found where Google will mistranslate an English sentence to a German sentence, that was still working until about a few months ago. So those are the instances where real life models, commercially deployed models, have been extracted, but no one has admitted to them firsthand.
Thank you very much, Ashkan. In the meantime, I've forwarded your the links you shared to the public chat. So all people attending the session and as login users can see now the links you indicated. So thank you very much. I think that then from your presentation, I've got the point that there are some issues we cannot solve. I mean, there are some trade-offs that probably we cannot address with the current techniques. So there is a part of the security and a part of the risk we need to accept, it seems, because we cannot achieve all the security functionalities that at the same time. So I found very interesting the speech from Marcus that talked about the usage of federated learning, federated machine learning to try to address some of them. My question to Marcus and to all is which impact this has on the reaction function. So from the speeches, I have got the point that you can try to cover detection and prevention, but then if things goes wrong and things can go horribly wrong, then what about the reaction? How the usage of, for instance, how the usage of federated machine learning can make the reaction more complex? I don't know if Marcus wants to comment on this.
Yeah, I think it's a difficult question because basically in this federated setting, you are have much less control over the whole system. So you can basically try to detect the models that have been poisoned or that's the first step. You kind of need to know that something bad is going on. Of course, then going back to a situation, but basically trying to unlearn, for example, something that is already in the model that maybe has been trained for a longer time. That's a kind of interesting and difficult question. So I know there are some research ongoing about this, kind of trying to create approaches where you could kind of take the model that you already have and unlearn some content that has been identified as potentially malicious. But I think there is still a lot of work to be done. With this federated learning, I think the main thought is that it provides significant benefits, or it can provide significant benefits in many use cases. However, practitioners should be well aware that they cannot just take a federated learning algorithm and deploy it without thinking about the security processes, because there are so many potential ways how this federated learning could be attacked, that you kind of need to think it through in your whole kind of security chain, that you try to at least limit exposure. And there are kind of technical means of defending, for example, trying to make sure that the data that are used for training are benign, or for example, using technologies like remote attestation to make sure that the algorithms that are running on the client side are actually doing the computations that they are supposed to do. I think, as Battista said, that there is probably no way to prove that, okay, my backdoor detection algorithm is now perfect and will detect all backdoors. I think it's this more like making a trade-off. What is the risk level I'm willing to live with, and what are the measures that I can basically reduce the risk?
Yeah, thanks, Marcus. I also think that a risk-based approach is always a very good one in security, while dealing with security. I don't know if there are comments from the other speakers on this point.
If you want, I can add just one comment. I also agree that we need, like, again, as in all cases, a top-down approach where you have risk management process on top, which helps you identify which attacks are relevant for your case and which are not, because you don't need to rule all of the attacks out in specific applications. And also another point that is worth mentioning is that machine learning systems are anyway statistical systems, so they tend to make errors even on natural data which is not maliciously perturbed. So you can have, I don't know, misclassification of traffic signs in benign conditions anyway, not necessarily if someone is going there and doing something bad. So we need also to develop policies to handle these cases, and perhaps exploiting, as in any kind of well-engineered system, exploiting redundancy of sensors and all these kind of additional detection mechanisms in place to understand if there is a failure, or to manage it, and so on and so forth. So I think this is something which needs to be built on top of all these attacks and defenses that we have discussed.
Maybe I can add something to this. So I think earlier we talked about the disconnect between academia and industry, that in industry there's not a wide enough awareness of the threats. I think this goes both ways. In particular, the academics are also not fully aware of how things are really deployed in practice, and they, it's very conducive for them to look at sort of individual problems like I talked about, rather than interaction. Similarly, it's conducive for them to look at impossibility results or challenges looking at individual attacks or defenses. But in practice, when a system is deployed, it's not just like a standalone defense, right? There's a whole chain of defenses, and just as they might have negative interactions, they might also serve as defense in depth. So the lack of communication goes both ways, and for example, impossible results are no reason to stop looking at something, because that just gives you better understanding. But in context, in a pipeline where there is a perimeter security, and whether there are multiple defenses that are deployed, even though specific defenses are shown to be impossible to achieve perfect security, you might still get reasonable enough security for the particular instance.
Thanks, Ejogen. Yeah, I agree on the fact that also building defense in depth is very good, a good way. The final question I want to throw to you is, to what extent the security testing of machine learning can generalize, so how easily this can be applied in large scale. Sorry. So, for instance, we are seeing applications of machine learning very widely spreading, and we are seeing attacks to this machine learning based system. So what are the main challenges you see in the generalization of the security measures, so security testing, for instance, and what can facilitate this process? I don't know if there's any comment to this. So,
well, yeah, if you want, I mean, some of these issues, I try to touch them on the presentation, but I think some of them can be automated in a very smart way. For example, if you have a model already deployed, you can generate attacks against it and save, let's say, this modified data somewhere. such that every time you update the model, you can check how the security behaves against this by just classifying this additional data set with attacks, basically. It's not the optimal attack against the new model, but gives you a rough idea and a quick estimation of how you are performing. So I think there are ways we can automate testing with an acceptable trade-off in practice, rather than having nothing as we have now. But of course, as I said, on top of this, we need better algorithms, better libraries. There is a bunch of libraries now that are implementing attacks, but again, it's something that doesn't scale maybe to the extent of practical applications, and it's also specific to images or audio. There's no more than there's not much more outside of these domains. As I said, there are ideas on how to generalize these, but we need some research on top of this to be carried out again. I think this is my idea, at least.
Yeah, I very much agree. And actually, if I can add something, because this is also something I'm interested in, I think that actually the attacks that are developed must be as much black box as possible. So like as much independent on the model, independent from the data as possible, such that they can be applied in many use cases. And in the end, it's not so, or at least for me, it's not so relevant to perform the best attack that run in the shortest time, make the minimal perturbation, because it's also this parallel between academy and industry. Actually, if you have just a malware detector, you don't care about how small modification the adversary doesn't care about how small the modification are, and actually how long it will take to generate this malware that evades detection. If it just take 1 week, he can wait 1 week and then just deploy it. But this is not a big constraint for an attacker, like having small modification, because in the end, like nobody looks at it. They are just automatically analyzed, and we don't care about evading a human that can actually see that there is something fishy there, because often it just doesn't go under the eye of a human, and that's why you have the machine learning model. So I think this should be the way. So making them these techniques or these attacks as black box as possible, and that they can be adaptive to any model, any type of data. And also what would benefit from that is that they can be used more during the design, and maybe comparing the performance and vulnerability of different type of machine learning models. So I can use a deep neural network, or I can use a random forest model, I can use an SVM, and maybe having the same attack that can run on all of these models, and seeing, each of them is vulnerable, and comparing the accuracy, we can basically choose the right trade-off of which model we want to deploy that will resist attacks and also be quite accurate at performing the task. So yeah, that was my point.
Yeah, I agree with you. But I mean, there is also another difference that we should make. Like, there are attacks which are weaponized at large scale, and these are like easier to detect, and those which will require more time and effort, and that's another story, right? So what I'm talking about is automating these attacks that can be weaponized on a large scale, and then it's interesting to see if your model can catch these easily, or if it fails immediately against these simple modifications. But I agree also about the story of the perturbation sites. It's a misconception in general, also for images. This arises from the fact, that in this initial paper, they said we can break the model with just an imperceptible perturbation, but it's not a problem. I mean, it's not really a problem in general.
Thank you very much, Battista, Samuel. Okay. I don't know if there are.
Maybe I can just
a quick
remark. So this is my pet peeve, that machine learning researchers want to keep this epsilon to be small in adversarial sample attacks because they only think about images. I think the reality is that there is a constraint on the attacker. Whatever the setting where the attacker wants to find an adversarial example, there is a constraint. And in the case of images, it might be perception, which is correctly or incorrectly represented by small epsilon. In the case of malware, the constraint of the attacker is that they have the original malware payload, and they want to find a perturbation that still retains this maliciousness of the payload. So I think we have to elevate this to a more abstract level where we say there is a constraint. The constraint is some sort of epsilon. In the case of malicious payload, the epsilon is maybe 0 because you don't want the perturbation to result in a non-malicious activity. How to then model that and how to sort of build that into the algorithm for finding adversarial examples, these are very challenging questions. But I think the spirit of the small epsilon is that there is a constraint on the attacker. And I think that is still the same. It's just that small epsilon is not even a good representation of perceptual indistinguishability, right?
But on this one, I think, so I agree with you partially in the sense that there is a constraint, because if there is no constraint, then the game is over. The attacker is going to win. So since there is a constraint on the manipulations, then we can play the game. For images, yes, you can think that if you have like the source image, you should only slightly perturb this, not to corrupt the signal. But there is cases where you have completely noisy images, which can be misclassified in a class with very high confidence. I also think these cases should be like avoided. Like if you have to say my algorithm is robust, it says there is a cat in this image, there has to be a cat, not just noise. So, I mean, this is just to give you an example where epsilon of the perceptibility constraint is not so relevant. But I agree with malware. And another thing I can say is that normally, I don't think there is a fixed epsilon. So what we should look at is how the algorithm behaves as you sweep this parameter. Because, and if you look at the all curve, because this gives you like the sensitivity of the approach to the strength of the modification. For malware in our studies, what we did was just check what happens as you increase the payload size. And then you see that some models, as you really add few kilobytes, they drop the performance completely. Some others stays like more stable, which is an indication, not that they cannot, be broken, but that they are more robust if the perturbation is small, at least, or to some, and it's better than having a model which drops immediately. So, of course, in the end, these are systems that you can break, I think. The question is making this harder for the attacker. You can play with more models which are less sensitive to changes. You can hide some information. You can do some practical measures like giving less feedback on all these kind of things. Of course, if you play in the white box case, you are gonna break them. There's no way you can be robust in this case.
Absolutely, I agree. I think I also agree that this small epsilon, which is then this is unspoken assumption that small epsilon means perceptual indistinguishability, is completely wrong, right? You can have small changes which are completely perceptibly distinguishable, or things like rotate the image, which can result in a very large epsilon, but it is still
well, one thing that we have to say is that these kind of threat models with small epsilon, they are still there because research is trying to show that at least in these easy mathematically tractable cases, you can get something robust, and still we are not able to. So if we step out of these simpler models, working with something more complicated, then it's even tougher. So I think that's just to say why people keep studying these things, right? That there is a motivation behind.
Thank you very much. So it seems there is still a lot to do, and that's good news for us as a research community. Okay, so before we close, I want to thank you very much, all the speakers, for the session, and all the attendees that follow us. You of course have the opportunity to link back to speakers within the B2Match platform. So please do it in case you're interested in a follow-up of this session. Also, I want to thank the BDVA and to organize Data Week 22 and that host and to hosting this session. And of course, Alexei Kirkienko, which co-organized it with me. So thank you very much, and have a nice day. Goodbye.
Thank you, Paolo and Alexei.
Thank you. Bye. It was nice to meet you.
Thank you.
Bye.